Okay, we are starting chapter 3, matter. We're going to talk about its properties and changes. So matter is defined as anything that has mass and occupies space. Everything is made up of matter. You are, the air you breathe, the pencil lead you're writing with. Matter is composed of building blocks called atoms. And matter exists in three main states. You have solids, liquids, and gases. Solids have a definite shape and a definite volume. So this pen is a solid. It has definite shape and definite volume. It is incompressible because the particles are already tightly packed, or the atoms are tightly packed. It has very strong attractive forces holding the particles rigidly in place, but the particles can vibrate around fixed points. Liquids have a indefinite shape, meaning they take the shape of their container, but a definite volume. And their particles can flow, so they can move past each other, because the attractive forces between the particles are not as strong as they are for a solid. And they are slightly compressible because there's a little bit more space between the particles. Gases have an indefinite shape and an indefinite volume. So that just means they're going to take the shape of their container. They are very compressible because their particles have much space between them. The particles can, they will move, they can flow, and they will move rapidly, and they have weak attractive forces, basically non-existent. Now we can take all of matter and we can classify it into two main groups. We can classify it as a mixture or a substance. Okay. Mixtures will always contain two or more different types of matter that can be present in varying concentrations. Each type of matter will retain its own properties. So think of salt and pepper. If you mix salt and pepper together, you can vary the amounts of each. You can see the salt, you can see the pepper. They can be separated by simple physical or mechanical means. So like filtering out sand from a mixture of sand and water, picking out peas from a mixture of peas and carrots, etc. Okay, there are two types of mixtures. You have heterogeneous and homogeneous. Let's talk about heterogeneous first. So the composition and properties are not uniform. They will always contain more than one phase. So if you're talking salt and pepper, you can see the salt phase, you can see the pepper phase. And a phase is defined as any region with a uniform set of properties. So if you have ice and water and the ice does not melt, you have two phases, the ice phase, the water phase, and actually you'd have the gas phase above. If you pour sugar into water and sugar settles on the bottom so that you can see it, that sugar would be a phase, the water would be a phase. The other type of mixture is called a homogeneous. And homogeneous will be identical, will have identical properties throughout, even under a microscope. So if you made some Kool-Aid and you dissolve the Kool-Aid in the water and you put a drop of the Kool-Aid on a slide, you cannot see the Kool-Aid particles. That would be a homogeneous mixture. It will have only one phase, but can have varying composition. So both of your mixtures can have varying composition or concentration. Sometimes we call a homogeneous mixture a solution, and a solution is made up of two parts. The solute is what is dissolved, and the solvent does the dissolving. So another way of looking at that, if you have a mixture of three different things, the one that is in a greater quantity would be the solvent. So if you have salt water, that would be a homogeneous as long as you can't see the salt particles. And then sugar stirred into water. Air, the air you breathe, is a homogeneous mixture. The other main type of matter is called a substance. And substances are defined as a particular kind of matter that is also homogeneous, meaning it's uniform throughout, but has a definite fixed composition. It will always have the same composition and properties in every sample. So that means no matter where you get that sample from, it's always the same. You cannot separate a substance into other substances without changing its identity and properties. There are two types of substances: the elements, and then if two or more elements combine chemically, that is a compound. So elements are composed of only one type of atom. So if you're talking carbon, all carbon atoms will have 6 protons. All oxygen atoms will have 8 protons, etc. It is the building block of all other matter. So you are made up of elements, as is your dog, and you cannot decompose elements by ordinary chemical means. A compound will contain 2 or more elements that are chemically combined in a definite or fixed ratio. For instance, C6H12O6, we talked about that last year in biology, is glucose or galactose or fructose. It will always have 6 carbons to 12 hydrogens to 6 oxygen. Now, with compounds, you have 2 different laws. You have one called the law of definite proportion, and then you have the law of multiple proportion. Definite proportion is just talking about one compound. So it's the elements of a given compound are always combined in the same proportion by mass regardless of a sample size. So what that means is it doesn't matter if you have 5 grams of NaCl or 50 grams of NaCl, you will always have the same proportion of sodium to chlorine. The law of multiple proportion, on the other hand, says 2 or more elements may combine in different small whole number ratios to produce more than one compound. So if you take hydrogen and oxygen, if you put 2 hydrogens to 1 oxygen, that is water. If you put 2 hydrogens to 2 oxygens, that would be hydrogen peroxide. So they contain the same elements, but they make a different compound. Now, when we talk about matter, we can talk about its properties. So properties are identifying characteristics of matter. And we have what we call physical properties and chemical properties, and then we can talk about physical changes and chemical changes. So we're going to start with physical first. So physical properties can be observed or measured without altering the identity of a substance. So some physical properties would be like color, melting point, I'm going to abbreviate that MP, density, boiling point, or BP, mass, its state, whether it's a solid, liquid, gas, etc. So your book will give you a list of them. A physical property can be further described as being extensive or intensive. If it is extensive, it means it depends upon the amount of matter present. So for instance, mass would be extensive. So the more you have, the greater the mass. Volume would be extensive. Energy would be extensive. If you have a large candy bar versus a small candy bar, the large candy bar is going to have more energy. Intensive property, on the other hand, are independent of the amount of matter present. So melting point, boiling point, density. So you may think, well, density should change with size. No, if you increase the mass, the volume also increases. So those are some examples of intensive properties, and these are some examples of extensive properties. And then we can talk about physical changes. And so physical changes are any change that does not change the identity or composition of the substance. So for instance, if you cut paper, you still have paper. If you grind a stone, you still have the particles. If you change the state, I guess I should say change of state. For instance, if you take ice and you melt it and it becomes water, these are both made of water, so change of state is physical. Then you have chemical properties and changes. A chemical property will describe the ability or the inability of a substance to undergo changes into a new substance, either by reacting with another substance or by decomposing. And so we'll be talking about chemical reactions. We'll be talking about what decomposition is in a later chapter. It will include words such as burning. So if you take paper and burn it, you cannot get it to go back to the original paper. Oxidizing, rusting, tarnishing, fermenting. You cannot get fermented milk to go back to normal. And then you have a chemical change. And I often refer to chemical changes as a chemical reaction. It is the process where one or more substances changes into a new substance. So if you have H2 gas plus O2 gas produces water, and this is not balanced, we call the things to the left your reactants. You can have one or more reactant, and this arrow means to produce or make or form. And then the things to the right are your products. You can have one product, as we do in this instance, or you can have multiple. The products formed will have different properties and reactants. So H2 is a gas, O2 is a gas. At room temp, they form water, which is a liquid. All chemical reactions will obey what we call the law of conservation of mass, and that simply means that the mass of your reactants must equal the mass of your products. So if I said you had 3 grams of hydrogen and you produced 8 grams of water, then you could determine how much oxygen. So 3 plus 5, so you would have to have 5 grams of oxygen to make 8 grams of water, okay? And then they must also obey the law of conservation of energy, and we'll talk about that in thermal chemistry in the spring, hopefully. Now, if you have a chemical reaction or a chemical change, there are 4 possible things that you'll look for. So, for instance, if we go to lab, we would look for the production of a gas, and that is shown by bubbling. The formation of a precipitant, which means you take 2 liquids, so maybe a clear white liquid, and a clear blue liquid, or I guess I should say a clear liquid and a blue liquid, and they get some little floaties, and that would be called your precipitant. And we'll do a precipitant lab in the future. And then if you have a color change, now you cannot just say color. Color is a physical property. Color change, there's got to be a change in the color. And then if the reaction gives off or evolves heat, sound, or light, for instance, a burning match, that would indicate that you have a chemical change. Now, the last thing for this chapter, this is a fairly quick chapter, is the introduction to a periodic table. So you should have access to a periodic table. Let's see if I can find mine up here. And on your table, you have periods and you have groups. So a group will go vertically, a period will run horizontally. Groups are also called families, and members of a family or group will have similar chemical properties because they have the same number of outer shell or valence electrons. So for instance, every element in this family here has 1 valence electron. Everyone in this family has 2 valence electrons. So you can look at the Roman numeral and it's going to tell you 2. The elements in this family will have 3 valence electrons. The family with carbon will have 4 valence electrons. The family with nitrogen will have 5. The family with oxygen will have 6. The family with fluorine will have 7. And the family with neon will have 8. And you may say, what about helium? Helium will not have 8 valence electrons. It will only have 2, but that shell is full. And so I would encourage you to get a periodic table, and we're going to write things on it. So when you look at your table, you have 7 periods, and they're numbered over on the side, 1, 2, 3, 4, 5, 6, 7. And these will have elements arranged according to their atomic number. So the atomic number, if you'll recall, is the number at the top. So hydrogen has an atomic number of 1. Boron has the atomic number of 5. The properties of elements within a period change as you move across. So they start out as a metal. So these are metals over here, and then they become more non-metallic in their characteristics. Then your vertical columns are called groups or families, and on your table, you're going to have those that are marked with an A. So these 2 families here and these 6 here, and then those marked with the B. The family with the A's are called main or representative groups, and the elements in these groups will have similar chemical properties because they have the same number of valence electrons, which we just wrote on our table. They won't have identical properties, but they'll have similar. They'll bond in the same fashion, etc. Now, some of these families will have names, so we're going to write the names here, and then I would encourage you to come back and write the names here, okay? So group 1A are called the alkali metals. Group 2A are called the alkaline earth metals. Group 6A are called the chalagens. Some people will put an extra C in here and call them chalcogens. Group 7A are the halogens. Group 8A are the noble gases. Some people will call them inert gases. And then the elements in the center with the B, these are called transition elements or transition metals. And we will not assign them a certain number of valence electrons because their valence electrons change with who you're putting them with. Okay, the next thing you can do is you can take this table and you see the stair step. Every one to the left are considered to be metals. Every one to the right are considered to be nonmetals. And then these that border the stair step are metalloids. So let's talk about the characteristics of metals first. So you have metals, which are generally shiny when clean and smooth. Now, if they have some corrosion, then they have to be cleaned up. They are solids at the room temp except for mercury. Now, your periodic table probably does not show it, but ours on the wall shows mercury and bromine. They're in a blue, and that means that they're a liquid. All of these in black would mean they're a solid at room temp. And then we have some of these down in here that are outlined, and they're white in the center. They are synthesized in a lab. Metals are considered to be good conductors of electricity and heat. Most metals are ductile and malleable. Ductile means that you can draw them into a string or a wire. Malleable means you can hit them into a sheet, like aluminum foil. They are located to the left of the stair step, so most of your elements are metals. As you go down a group or a family, we say they become more metallic. So cesium would be more metallic than lithium. Strontium would be more metallic than beryllium. That simply means that the valence electrons of strontium are easier to be given up than those of magnesium because they're further from the nucleus, not as strong a pull. And then you have nonmetals. Their state is they are usually gases, or if they're solid like carbon and sulfur, they'll be a dull, brittle solid. Bromine is a red liquid. They are not good conductors of electricity. They are poor conductors, and they're located to the right of the stair step. And then those bordering the stair step are metalloids. Sometimes we call them semi-solids. Many of them will be brittle solids at room temp, and they'll have properties intermediate between metals and non-metals, so we call them semiconductors, okay? So if I were you, I would come back to my table, and just so you would have, you'll put a lot of things on this table in the future, but I would write above Group 1A, these are the alkali metals, and then alkaline earth metals, etc., okay? And then if I were you, I would mark my metalloids. And so I would put a little star in boron's box, and then silicon below it. And then on either side, 3233, germanium and arsenic. And then 51 and 52, antimony and tellurium. And then 84 and 85, polonium and astenine. And I would make a note up here that these are considered your metalloids. So there should be 8 of them. 1, 2, 3, 4, 5, 6, 7, 8. So that is it for Chapter 3. And so you can work on your study guide. Thank you.